We can think about the vector as a tool or some sort of entity like we did with numbers, and then we do some basic operations. And then we'll take a look at different functions as those entities, and then we'll do some basic operations on those. And more complicated calculus operations like derivatives and integrals. So this is just another type of operation for vectors. Now the thing about this is that this really only works for 3 dimensions. There might be some other special cross product defined for 4 or 5 dimensions, but it doesn't easily extend into higher dimensions like the dot product did. It probably would become more complex matrix, yeah. So for those people that have taken linear algebra, the idea of a determinant should be familiar. And if you haven't taken linear algebra, we'll talk about it. The definition of the cross product is some complicated looking thing. By the way, the cross product is sometimes known as a vector product because the result is a vector. So the definition of the cross product is this complicated looking scenario where you have 3 components and each of those components look kind of different. But if you try to break it down using matrices, it might help a little bit. And the matrix uses the I, J, K unit vectors that we saw the other day. And the way matrices work is that they expand. If you want to find the determinant of the matrix, they expand on a specific row or column. And we have this set up to be able to expand on the top row. And so the way they expand it on the top row is that they look at the first component of the matrix, the top upper left-hand corner, and then they take the submatrix that's left over and they find the determinant of the submatrix that's left over. So the submatrix that's left over has 4 numbers, and then the way to find the determinant of that is to multiply. The diagonals would be the diagonals going down from the upper left-hand corner down the diagonal. So you multiply the diagonals, that's a sub 2, b sub 3, and then you subtract the other 2 numbers, and for a 2 by 2 matrix, these other 2 numbers are called the wings. B2, A3. Yeah?
Probably easier to tell people to cover up the I column with the finger and then multiply what's there available. I thought that was more easier for me to learn.
Okay, so the other option is to, if you're expanding on the upper right-hand column, you would cover up the first column, or the first row and the first column, and what you have left over will be your submatrix. Yeah, well, it is easier.
Yeah.
Now, the thing about expanding on a matrix is that when you get to the next number, there is a sign change, and that becomes negative. So imagine taking J now. I would cross out the first column because J's in the first row because J's in the first row, and I would cross out the second column. And what I have left is A1, B1, A3, B3. I don't know. Maybe I'm writing too much on this. So A1, B1, A3, B3 is what I have left over. But there's still a negative sign in front of that. And it turns out that when you're doing this determinant expansion, you're actually assigning a sign for each of those components that you're expanding. And so in our last one, when we take our K, we would cross out that first row and the last column, and then what you would have left is A1, A2, B1, B2 in the K, and this has a positive sign to it. Okay? Yeah? Because it alternates. The idea of finding a matrix, a determinant of the matrix, alternates signs. I don't know if you want to look at yet another way to do this using the matrices, but this is I've seen some people do it this way as well. Although sometimes when I see this done on a quiz or on a test, they get it wrong. I don't know. So A1, A2, A3, B1, B2, B3. And so what they do is they expand or extend this and add the first two columns again. So I and J column again. A1, A2, B1, B2. And then they look at the diagonals, and then they multiply all these. I missed that last B. So they would multiply all these and add it, and then they would multiply these diagonals and subtract it. So let's see what this will give us. That would give us A2, B3 times I plus A3, B1 J plus A1, B2, K, and then there's B1, A2, K with a negative, and there's another negative B2, A3, J, or that's an I. And then another minus B3, A1, J. And if you check this, it should be the same. I hope. Let's check the I's. So the I is A2, B3 minus B2, A3. A2, B3 minus A3, B2. Same thing. Okay? All right, so it might be good practice if you try some. So let's try some examples. U and V, where U is equal to, let's say, 1, 0, 4, and v is equal to -3, 4, -5. All right, take a couple of minutes to try it out, and then I'll do it, and hopefully our answers will match. No, let's wait for other people too. So I got that first submatrix, 0, 4, 4, -5. Now remember that the J has a negative in front of it. And then now the submatrix that goes with that, if I look at the J component, is going to be 1, 4, -3, -5. And in the K component, it's just 1, 0, -3, 4. Now, for each of these, I would do the multiplication of the diagonals minus the product of the wings. So that's 0 minus 4 times 4 is 16 in the I direction. And then don't forget the negative sign. I have a -5 minus -3 times 4 is -12 in the J direction. And then a 4 minus 0 in the K direction. So -16I, this is a +7 with a negative in front. So it turns out to be -7 J plus 4K. And sometimes if you want to switch it around to a different notation, did I do it correctly? Look good? Okay. So I know that was only one time, but you guys are now experts in this, right? Practice. So practice. Go and practice, and then practice some more. Just carry a little notepad with you, and whenever you're just sitting there waiting for the bus, just write down a couple of vectors and cross them. All right, something interesting about the cross product compared to the other vectors that you crossed them with. What? The result of the cross product compared to the two vectors that you crossed them with is that, well, let's take a look. You have one. If you dot it with the result, if you dot one of the vectors that you cross with the result of the cross product, there's something interesting that happens. So this is equal to, what is it, negative 16 plus 0. Remember, the dot product gives you a scalar, right? Negative 16 plus 0. 4 times 4 is 16. So it seems like it might be a coincidence. Let's try the other one. Oh boy. What is it?
48.
So positive 48 minus 28 minus 20 minus 20 0. Is this 0 vector or 0 scalar? This is scalar. The dot product results in a scalar. So, yeah, it turns out that the vector that you get when you cross two vectors is actually perpendicular to those other two vectors that you crossed. So that turns out to be an important theorem for us.
And it's the dot product is only 0 when the vectors are perpendicular?
If it's perpendicular, then the dot product is equal to 0. So, turns out that, remember the word orthogonal means perpendicular? So vectors, the vector A cross B, that's the resulting vector you get from the cross product, is perpendicular to both A and B. And to prove that, we did an example that's not exactly a proof. To prove that, what you could do is you can let A equal to A1, A2, A3, and then you let B equal to B1, B2, B3. And then you perform the cross product on this, which is actually the definition, right? It's right here already.
Can the cross product work for the vector that doesn't have 3?
Oh, we'll take a look at that in a minute. So I'm not going to do it, but perform the cross product. And then after you get the cross product, you dot it with A and B separately. And then you'll see that you'll get 0 both times. You'll get those combinations of A1, A2, A3, B1, B2, B3. You'll get them to all disappear, and then it'll become 0. What? Well, you cross these two, period, and then dot it. Semicolon. What? Cross, then dot. It's like the sign and drive event commercial. You can't sign and drive, it's sign and then drive. Cross and then dot. Whatever. All right. So trying to find the cross product of something larger than 3 dimensions is a little bit over what we want to talk about. But there is something interesting to say about a 2-dimensional vector. And it turns out that we can cross two two-dimensional vectors together. So let's take a look at that. Cross of two vectors in R2. So let's take a look at some arbitrary vectors in R2. Let's call them A1, A2, and then B, B1 and B2. Now, because of the formula, we're kind of necessarily having to look at this in 3 dimensions. And so to kind of force the issue about looking at this in 3 dimensions, well, we simply insert some zeros for the z component. Because if you look at the 2-dimensional plane that we're looking at, xy, that actually lives in 3D, except we're looking at it flat, xy. Right? So the 2 vectors that are hanging out in on the xy plane can also hang out in 3 dimensions on the xy plane. They would just have a 0 component for the z. All right? So imagine, before we do this computation, imagine these 2 vectors on the plane. What happens when you cross them? When you cross them, you're supposed to get a vector that's perpendicular to the other 2 vectors, right? So what happens when you cross them? Which way is the vector going? Let me rephrase the question. How's the vector going to look like? Let me rephrase the question. The vector will be parallel to what?
Z.
The z-axis. Now, it depends on how you cross this, whether it's going to be pointing up or pointing down. So that we don't know. But if it's going in the direction of the z-axis, either going straight up or going straight down, what can you say about those vectors, or that vector that's either going straight up or going straight down? It's perpendicular to both of them, but what can you say about the vector itself? Z-axis, so how does the vector look like? How does the... Yeah, that's what I was trying to say. How would I ask that question? So the answer is, your vector would look like 0, 0, a number. Well, not necessarily a unit, but it's just only has the one component in the z. That's what I wanted you guys to say, but I wasn't asking the right question. How should I have asked the question? The coordinates? What are the coordinates of the vector? Good. Thanks, Gabriel. Yeah, without actually computing it, which is what we're about to do, just to prove that the x and y components are going to be 0. All right, so let's do the cross product of these 2 vectors, modified into 3D. So we got A cross B is equal to ijk, A1, A2, and then the third component for both of these vectors would be 0, B1, B2, and 0. So now we do the cross product. We get, you guys are experts, right? So I have A2 times 0, B2 times 0. So that's 0 in the I direction. In the J direction, I would cross out the second column, A1 times 0, B1 times 0. So that's 0 again, negative 0, same thing. And then in the K, this is the only one that's really going to matter, is going to be A1, B2 minus A2, B1. And that, provided that they're not all equal to 0, this would be your only non-zero term. So it's 0, 0, some number as a vector goes straight up or straight down.
For
It kind of looks like a 1, huh? Yeah. Thanks, Martha. Okay. So there are going to be some times that are going to be kind of strange to say, oh, we want to cross this vector, but it's only in 2 dimensions. So we could just throw zeros in there. We'll see that a cross product of 2 vectors on the plane will give you something that's perpendicular to the plane. And so in this case, because the plane is flat on the xy plane, then it's just going to be 0, 0 in the first 2 components. Pardon me? Order matters in cross products. Yeah. Yeah.
Okay, so it's switched around, not it's A1 B2 minus B1 B2.
Yeah, A1, B2 minus B1, A2. Oh, yeah, this because this is regular multiplication, it doesn't matter. B1, A2. It's the same.
As long as you're not moving the negative around.
Yeah. Okay. All right. Yeah, well, I should have made this a point. Frederick just reminded me of something. If we take a look at this, these 2 vectors again, we crossed it. We crossed U cross V, and then we got this vector for an answer. Let's do the same thing. Let's do the same vectors, and I'll have you do it again. But let's switch the order. So this time, let's compute V cross U. So go ahead and give that a try. I'll do mine slowly, and then we'll compare answers. Yeah.
So B cross U is not the same as B cross B, correct?
That's what we're trying to figure out.
Okay,
All right, so I think the vector that we're trying to get here is, let's see, 16 minus 0, 16 in the I direction. We have a negative here. This is negative 12 minus 5. So negative 12 minus 5 is negative 7 with a negative in front. So positive 7J and then 4K. Negative 4K. So if we compare this to the result that we got last time, u cross v was -16, -7, +4. And we see that this is the exact opposite. And that's another not coincidence. It's always going to happen this way. So here we've just uncovered one of the important properties of the cross product is that u cross v does not equal to v cross u. Instead, it's equal to its negative. And without the negative sign there, if they were actually equal to each other, the u cross v and v cross u, then it would be considered commutative. The fact that this is equal to a negative actually has a special name for it, anti-commutative. Say that they're off by negative sign. Okay, so that's one of several properties that we'll see for the cross product. Somebody's messing with my Dropbox. It keeps popping up. Professor Menares says we have a meeting at 2:30, so he's messing around with my notes. So let's take a look at more properties. Oh, I guess before the properties, I should write down my notes so I can go in order of my notes instead of jumping around. Now, there's this definition that describes the geometric property, a special geometric property for the cross product, and it's very similar to the dot product property, the geometric property of the dot product. But I have to say that whenever you're asked to find the angle between two vectors, try to use the dot product. I think the dot product is used about 95% of the time when they're finding the angle between them. You only do the cross product whenever either the cross product's already computed for you or I don't know what else. I mean, if you're going to dot a vector versus dot two vectors versus cross two vectors, the dot product is way easier, right? So that would be motivation enough to stick with the dot product when you're trying to find the angle between two vectors. But nevertheless, this still does exist. And if we want to find the angle between them, the two vectors is theta, then there's a relationship between the cross product and that angle theta. And remember that the result of the cross product is a vector, so we have the magnitudes of A and B as scalars and the sign of any number is a scalar, so we want a scalar representation for the cross product, and that's just the magnitude of the cross product. So it turns out that the magnitude of the cross product is equal to each of these things. And so if the two vectors are parallel, either pointing in the same direction, in which case theta would be equal to 0, or pointing in the exact opposite direction, in which case theta would be equal to pi, sine of 0 and sine pi are both equal to 0. So it turns out that the cross product of two vectors that are perpendicular or parallel. Oops, it's not a pen. If the two vectors are parallel, then the cross product of them would be equal to 0. Notice a little arrow on top of the 0. Okay, the length of the cross product is also some geometric importance, and that's the area of the parallelogram spanned by A and B. We talked about the parallelogram spanned by A and B. At least we talked about the diagonal when we talked about addition and subtraction. I don't know if you remember. But if you have two vectors, A and B, or U and V, or whatever, they span a parallelogram if you do that head-to-tail thing like we did with addition and subtraction. And so this area over here turns out to be the area, well, let's figure out what that area is. Do you guys know how to find the area of parallelogram? It's base times height, except since this is kind of slanted, the height has to be changed a little bit. So this is the height over here. Yeah, you can think about it as adding the area of two triangles, but that's if the triangles are, if this was exactly lined up in the perpendicular, because now if it's not, then it's not quite two triangles. No, parallelogram is four sides, two are parallel to each other. Well, it'd be hard to have four sides parallel to each other.
No, I mean,
Oh, not quite. So let's find the area of the parallelogram here, and B for base is not a good letter. Base times height. Let's call this, what should we call this? Base. It's base times height. That's the area of the parallelogram. So the base happens to just be the magnitude of A, right? Now, the height, we don't know what the height is, but the height is kind of dependent on A and B. Kind of looks like this thing. Oh, wait, what if we drew a triangle here? So the theta is the angle between A and B, and that seems to be the opposite side of H, right? So I want to know what H is. I know that sine of theta is equal to the H opposite over the magnitude of B. So that's just magnitude of B sine theta. Well, base times height, this is your base, this is your height. Base times height is equal to magnitude of A, magnitude of B, sine of theta. But that's the definition of the cross product, or that's the cross product, the magnitude of the cross product. Okay? The A's and B's in the vector drawing here. Where else? This one, yeah. Yep. Let's make sure that it's vectors. Yeah.
So cross product is 0. The dot product is at its max, and vice versa.
Yeah. All right, one more thing that I forgot to say is that the cross product, you know, because one of them is negative, one of them is positive, if you switch the order, turns out that it depends on the right-hand rule again. So the cross product depends on the right-hand rule. So let's make a note of that. Cross product follows the right-hand rule. So if this is U and this is V, and this is the smallest angle between them, then the cross product would be going up perpendicular to both u and v. U cross v. And then if you switch to order, it would be the same length, except it would be going down, v cross u. Okay? All right, one more page of properties of cross product. So I'm not going to talk about this too much. I'll mention that the first one is the anti-commutativity, and then there's this combinations with scalars and vectors and stuff like that that happen to be true. So whenever this thing comes up, I'll try to remind you that this came from the properties. And in 3 dimensions, in 2 dimensions, you got 2 vectors can span a parallelogram. In 3 dimensions, 3 vectors can span like this 3-dimensional slanted cube kind of object. And so that turns out to be what's called a parallelepiped. Just to give meaning to one of these properties, number 5, this actually is a geometric quantity that gives you the volume of that 3-dimensional slanted cube. So if you have 3 vectors, put them all tail to tail, then this thing will span what's called a parallelepiped, a 3-dimensional slanted cube. And this gives a volume. Not so much, but it's just a good geometric example of something. Another application of the cross product. So the last application is a application in physics, torque. If you guys want to know more about that, go ask Attila. Professor Altero. And you guys have homework on that, so you should look at the example and look at the lab. All right. I think we got some vectors down, some vector operations, addition, subtraction, multiplication, 3 types of multiplication, scalar, dot, and cross. And then now we're ready to put it all together to make something more meaningful, mathematically meaningful with these vectors. Okay, that's it. You got some homework due on Sunday, and then some labs due before that, so you can figure that out. See you guys on Monday.